Hello everybody. Today we will discuss a pretty interesting problem about charged particle drift in a magnetic field. So, before that, please subscribe for this channel. In that case, that could be available a new problem almost every day. Magnetism, charged particle drift. Near a long straight wire carrying a current I, a particle with a charge Q and a mass m was placed at a distance r0 from the wire, and the particle was given a speed v0 directed against the current. There is no gravity. So first question, find the minimum and maximum distance of the particle from the wire while moving, and what distance from the wire is the velocity of the particle directed perpendicular to it. And the second question, find the drift velocity u of the particle, that is the displacement velocity along the wire of the maximum and minimum points of the trajectory remote from it, provided that coefficient alpha represented here is much smaller than 1, very close to 0, where mu0 is the magnetic vacuum permittivity. So first let's draw the picture of this process. On this picture we have coordinates x and y, and we have wire which is on coordinate x equals 0, and the current going down. Our particle is here on distance r0 from this wire to the right, and the velocity is going up, parallel to, I would say, anti-parallel to current. And because we have this picture, we have magnetic field in this plane of our picture. It's going out of this page. So in that case, if we have velocity going up, magnetic field is going to us, so it means that force is going to the right, and our particle will move clockwise. So let's answer for the first question. Find the minimum and maximum of the particle's distance from the wire while moving. At what distance from the wire is the velocity of the particle directed perpendicular to it? Solution. As in many cases, here we have to write good equations for motion and choose proper coordinates, and see that probably proper coordinates, it's x, which is distance from wire. Also we have y, which is direction of drift, and also we have a good variable, which is angle between vertical and the current velocity of this particle, which is changing. So let's write equations connecting all these three variables. So first obvious equation, we have dx equal v0 multiplied by sine phi and multiplied by dt. Second obvious equation is dy equal v0 cosine phi and dt. And the last one is a change of our velocity. And because this particle moving in a magnetic field, it means that speed of this particle is constant, and only direction of velocity is changing. And we can write equation how is this direction is changing because acceleration is perpendicular to velocity. I would say it's normal, and this is the expression for the change of this direction, where a is acceleration. This acceleration could be found from force acting on our particle, and we know that in our case, because our magnetic field always perpendicular to velocity, we have force equal V0 QB, where B is a magnetic field created by this current. And also we can write the expression for magnetic field created by infinite wire. This is the expression for such a magnetic field. Here we have mu0, that's a magnetic constant, I is current, and x is a distance from this wire. Now when we have all formulas, we can find acceleration dividing force by mass of this particle, which will give us this expression. This is our expression for this formula. Now we can cancel speed and just replace this formula with this expression. Probably this is all what we need to solve this problem. Let's take a close look for these variables. We have 4 variables, and we can exclude some of them, because in this formula we have dt, and in this formula we have dt, and also we don't have a y coordinate here. So if we take dt from here and insert it in here, we will get a equation connecting x and the angle phi. That's good. This is our equation. And now we can split variables and integrate this equation. Now we can do integral for both parts, and we see that limits for integration are the current x position and the initial r0, that's on the left, and on the right we have initial position is angle phi equals 0, and final is just current angle phi. So after integration we have this expression. Now we can rewrite this expression in the form of x as a function of angle phi. Now we have expression for x as a function of phi, and we can answer for the first question. So to minimum of this function we have when cosine phi equal 1, and the maximum when cosine equal -1, which is in the first case we have our initial position when particle going vertically, and when cosine equal -1, particle going down, and that's furthest position. And when a particle going straight parallel to x or perpendicular to y, we have cosine phi equals 0. That will be this position and this position. That will be the same meaning when cosine phi equals 0. And let's write these expressions. So we have x minimum equal r0, x maximum equal r0 multiplied by this exponent, and x moving horizontally when we have this r0 multiplied by this expression. And let's write condition for this expression. We have that coefficient alpha equal this expression almost 0, a little greater than 0. So it means that this exponent from small alpha, and this is very small. So it means that our particle moving with a very small, almost circle trajectory near from R0. So R0 is much greater than radius of this trajectory. And this we will use later for the second question. So we just answer for the first question. Second question. Find the drift velocity u of the particle, that is the displacement velocity along the wire of the maximum and minimum points of the trajectory remote from it. Provide that this coefficient much less than 1, where mu0 is a magnetic vacuum permittivity. So now let's take a look for this expression dy. We already solved our equation using x, and we can insert this x in third equation here and express dt as a function of angle phi, and put it here. In that case we will have an equation connecting y and angle. This is what we need. So we have expression dt as a function of angle, and we can insert this dt in this formula, and we will get dy. So we have an expression for dy as a function of cosine, and we could integrate this expression, but this function, it has no straight integral in straight functions. But now we can use this estimation, that coefficient, this coefficient much less than 1. It means that this exponent we can represent as an exponent for very small argument, which is approximately equal 1 plus this argument. And we can rewrite this expression like this. Now we can integrate both parts. So we have approximately this expression, and let's take a look at this. Here we have cosine phi, and the integral from cosine phi, its periodic function, and from angle 0 to 2 pi, that will be 0. And only cosine square phi will be positive, so that will be non-zero element for this integral. So we can represent this dy as this one. And now cosine square from phi, that's 1 plus cosine 2 phi over 2. Again we have cosine from 2 phi will be 0, and then we have only integral from 1/2 in limits from 0 to 2 pi, so that will be pi. So total displacement for one period will be this one. And now we have to calculate what is the period. For that we can use this expression. We see that x is almost equal to r0. We can put this r0 here and do integral. Again, that will be from 0 to 2 pi, and here will be total period. So we have this expression, and now we can write what is dt for one period. That will be this expression. And now we have a last step. We have to find what is our speed drift. That will be dy over dt, which is this expression. Let's answer for question 2. So our drift will be in a negative direction, and almost like circular orbit. That will be some kind of spiral. So that's it. This is the answer for the second final question.